with an interesting class today. So we're going to continue with our discussion of various elementary but concepts that will end up being important to us in projective space. But before doing that, I just want to back up for a moment, just to sort of put our grand project to check in on how we're doing with our big question, because already our sort of very big question from the first couple of lectures was we are thinking about scattering amplitudes. They depend on some on-shell data, and normally we get them by summing Feynman diagrams, but we see all these structure in them. There's all these hints that somehow they should be the answer to a different kind of question. And the question should live in the kinematic space where the amplitudes are defined. So we can think of it any way of thinking about the sort of boundary of Minkowski space, but our sort of grand challenge was that it's not at all obvious what to do there. There's no obvious notion of locality, time, blah, blah, blah. Okay, so now, then we played for a little while. We were responsible with symmetries. We figured out how to think about the kinematics properly. Something magical happened so that we could determine amplitudes for gluons and gravitons recursively by the BCFW method. And we started seeing that these were much, much simpler answers, but the answers had these peculiar properties, that the BCFW representation gave you these incredibly tiny answers, short answers, but each term didn't look like it came from local unitary evolution in space-time. Each term had spurious poles that sort of magically cancel in the whole sum. And furthermore, each term manifests this hidden, remarkable dual conformal invariant that the theory of gluons has anyway. And we can suitably supersymmetrize everything, but at tree level, these are all even properties of ordinary gluons in the real world. So if we just take stock for a second, now in this, once we have a sort of sharper idea of what some of these amplitudes can look like, we can see that these sort of fuzzy grand questions already become something much sharper that you can actually think about and to work on. So let me remind you that the formula we ended up having. So now the kinematic variables that we're talking about are the momentum twistor variables, at least for now. We'll go back to talking about ordinary lambdas and lambda tildes for most of the rest of the month. But we have these things that depend on these z's, and we had this formula that came from BCFW, which was this remarkable thing involving this 5 bracket, where this basic object 1, 2, 3, 4, 5 was 1, 2, 3, 4, eta 5 plus cyclic to the 4th over the product of all these brackets. Okay? And so here, already in this limited context, we can ask our sort of grand questions again for this specific question. Now, what is our data? Our data is a bunch of 4 vectors, z1 through zn. They have a cyclic structure, so that much we know, right? They're not just randomly given. They have an ordering on them. But that's almost it. We just have like n 4-dimensional vectors. It's supersymmetric, so we have n 4-dimensional etas that go along with them as well. Okay, so that's our data. In the space of n z's and n etas with an ordering, somehow you have to ask a question that has that as its answer. All right, that's our aim. And what are some qualitative properties? So some qualitative properties are, so first of all, as we stressed, this breaks the symmetries. This breaks the cyclic symmetry, right? There's a 1 that sits in front there. But the particle 1 isn't special here. So this is one representation. There are many representations. In fact, I can replace this 1 by any of the particle species. Okay, and it would get the same answer. So whatever it is, at least if this representation is a clue, there shouldn't be any one privileged way of getting the answer. There should be lots of ways of getting the answer. Every way somehow is built out of pieces that has spurious poles that cancel in the sum. What's an invariant statement? An invariant statement is that where are the only poles? The only poles are when these brackets I plus 1, jj plus 1 go to 0, right? And that's already something which, if I just give you of n ordered z's, how the hell do you know that something interesting happens when I plus 1 and jj plus 1 line a plane together, or when the line I plus 1 intersects the line jj plus 1? That is exactly space-time locality, right? Because when we then translate and say the lines I plus 1 correspond to points in space-time, then we're saying when the 2 points in space-time become null separated, something interesting happens. But I'm not giving you the points in space-time. I'm just giving you n z's with an ordering on them. So how the hell do you know that this structure, I plus 1, jj plus 1, has got to somehow be important? And the poles have got to know about this interesting combination. Okay? So it's interesting that already in this more limited setting, you can ask a much sharper version of this question. For example, you can ask, let's take these basic objects, these 5 brackets, and let's just ask, is there any way of putting them together so that all the spurious poles cancel, right? Is there any way of putting them together so that only I plus 1, jj plus 1 shows up? So that's now an algebraic problem. And the remarkable thing is that it's unique. There's a single way of putting them together. So the answer is not 0, and that all the poles cancel out. That single way of putting them all together is the amplitude, right? And of course, it has many representations of it because there's many identities that relate them to each other. Okay, but I'm just stressing this so you see that we now have sharper questions. Now we want to know, with these variables, with the z's, we somehow have to produce a structure which only has poles when I plus 1, jj plus 1 goes to 0. Furthermore, it has to factorize on those poles. We're not talking about factorization here. This is a little too small for us to see the physics of factorization in a simpler way. But more generally, we have to see that as the poles in the right place, it factorizes in the correct way. We even have some idea of what the building blocks are from BCFW recursion. And so this question is starting to become more sharp. Well, what is this object the answer to? What question posed in the space of Z is this object the answer to? Okay, and I want to give you also a kind of a toy version of this that we're going to keep in the back of our mind for this class. And later we'll come back, of course, and do the whole shebang. But here's a toy version of it. A toy version, instead of having sum over I and j, is just going to have a sum over just one I. Okay, and instead of being a sum over I plus 1, jj plus 1, will just be I plus 1. So this is m toy and of n, and also k equals 1. And now my data is also going to be some z's. But these z's are going to be 2-dimensional rather than 4-dimensional. So these are z's and etas that are 4 vectors. And these are going to be z's and etas that are 2 vectors. Okay, so I is going to run from 1 to 2. A is going to run from 1 to 2. And so my toy amplitude is going to look almost the same as sum over I, 1 I plus 1. And the only poles will be when I plus 1 goes to 0, and this basic bracket is going to just be the analog of that. But just 1, 2. These are now 2-dimensional vectors. So it'll be 1, 2, eta 3 plus cyclic squared divided by 1, 2, 2, 3, 3, 1. Right? So it's a smaller problem. We have 2-dimensional vectors, not 4-dimensional vectors. It's sum over I, not the sum over ij. But it has the same feeling about it, right? I have some z's. The z's are just ordered. Somehow I have to know that only I plus 1 comes out and matters. And also, there's representations of the answer in many different ways that break the symmetries, right? But the final answer is the same, and there's also a unique way of putting these things together so that this is the answer. Okay? And so, and the setting is now the space of 2-dimensional vectors. How much simpler? You can visualize it. We don't have to think about anything. Just a space of 2-dimensional vectors and a bunch of etas. Somehow we have to ask a question in that space whose answer is this. All right. So keep that in the back of your mind. This is going to be our sort of goal for the next month. Okay. So is to ask this question in this space, back in the original momentum space. All right. And so this is the big picture goal of this entire program. But specifically, we're going to be playing with twistors and momentum twistors and asking this question about gluon amplitudes. Okay? I told you last time about some very elementary things about projective space. One of the motivations is that the momentum twistor variables are objects that live in P3, or twistor variables live in projective space. But we're going to just play a little bit more in projective space because it's going to turn out that it's questions that are naturally posed in projective space and slightly larger cousins of projective space, the Grossmanians, that are going to be the kind of question we have to learn to ask whose answer are these interesting objects. Okay? And part of the delightful thing here is that all we're doing is generalizing thousands-of-year-old ideas. Okay? We're just going back a few thousand years to the Greeks to think about areas of triangles and so on, and polyhedra a little more generally. And it's really a set of ideas that is continuously connected to sort of 2,000 years of intellectual history that brings us to the sort of thing that we're talking about now, rather directly. Okay, so now let's go back and pick up a theme that we talked about at the end last time, and I'll just say it again. Let's talk about volumes in projective space. And as we said, the notion of a volume does not make any sense by itself. You need some plane at infinity, right? So it's an affine notion. The notion of a volume does make sense as an affine notion. Now, in the previous lectures, I was calling that hyperplane at infinity or line infinity L infinity. Almost forevermore in this course, I'll be replacing it by y. Okay. So y is my plane at infinity. The downstairs index is my plane at infinity. Okay, so let's talk about the simplest example. What is a 1D volume? So if you give me just 2 points, I don't know, xb and xa, then this difference, xb minus xa, is the volume of this interval. xb minus xa is invariant under the affine transformation. So the full SL2 transformations are the symmetries of P1, but the thing that leaves the line at the point, in this case, a point at infinity, the line infinity fixed, is just the translations. Okay, so xb minus xa is translationally invariant. But how do I write this in a projectively friendly way that makes it manifest that that's what I'm doing? Well, the x's are, in this language, would be 1xa, where I've put y to be 1, 0. Okay, so when I draw this picture, that's tacitly what I'm doing. I'm putting the line at infinity to look like 1, 0, and I'm putting a 1 in front of everyone. Okay, so then this expression is this, first of all, this determinant 1xa, 1xb, which is xb minus xa. But this is really capital Xa, capital XB over y dot xa, y dot xb. Okay, so that's our first volume. And you see, we need the y. The weights in A and B cancel. And it has a weight in y. It has an overall weight in y, and that's fine. Volume has units. Okay, so that's what tells us that volume has units. Okay? Sorry? Yeah, and upstairs, everything we ever see in a bracket is a determinant. So now it's just contracting with the epsilon symbol, so we're just contracting xa and xb with the epsilon symbol. Here, yeah, because the x's have upstairs indices and these have downstairs indices. Okay? Okay? All right, so now let's move on to a triangle. So this is the example we did last time. So let's say I give you the corners, just again, naively two-dimensionally as xa, xb, xc. Then what is the area of the triangle, ignoring the factor of 2, a half, is this determinant. That's what you learned sometime in junior high school or high school, right? But what is this? This is xa, xb, xc over y xa, y xb, y xc. all right, and so on. So we know what the volume of a simplex is in general is of a simplex in Pn is x1 through xn plus 1 over y x1 y xn plus 1. All right, and just as a tiny piece of advice, it's often useful when you draw these pictures. Of course, I told you, you can visualize everything by just drawing pictures in the plane. You'll never get anything wrong, right? But it's actually useful if you have an infinity, if you have an interesting line around, to sort of draw that in your picture and not put it at infinity. Okay, you could put it at infinity, but it's actually useful to sort of draw a y here, draw your triangle here, okay? And let's just see why this is, let's just see what we learned from this, for example, here. So, and that's kind of be one of the novelties of what we're going to see when we're going to come back to in a month or so when we start talking about the amplitahedron, or 3 weeks or so, I hope, is that our variable of interest is going to be this y. Okay, so we're going to, in the conventional point of view, we're going to be moving infinity around, right? That's part of the reason it's useful to keep it around alive in our minds as we're thinking about these things. But let's just do some very elementary things with this. For example, this expression has a pole when y dot x equals 0. When we do our gauge fixing to go to this form, we've made that impossible, right? When we make that gauge fixing, we're like setting the top components to be 1. We're making that impossible. The actual thing has a pole. So what is the interpretation of this pole? What does it mean when, like, why is this area of the triangle blowing up when yxa is equal to 0? Right, all we're doing when we say that yxa is 0 is we're taking this point and we're moving it to infinity, right? So it's obvious. You take your triangle and you're just turning into a triangle whose area is infinitely large, right? So those poles are quite obvious. All right, let's actually also write this formula in another way. Let us imagine that instead of giving the vertices of the triangle, I gave you the edges of the triangle. Right, so now we draw the same thing. But let's say I've given you the edges, and I'm just going to give the edges names that will be useful for me later. Okay? So the z's also have downstairs indices. These are now edges. They're lines. So that's z1i, z2i, z3i. Okay? Now what is the formula? I still have some y at infinity here. Well, now we don't have to think, right? It looks like 1 over y z1, z2, y z2, z3, y z3, z1. Downstairs and upstairs, it has to have a z1, z2, z3 all squared. Okay? And it's squared just for the weights to be correct. All the weights in 1, 2, and 3 have got to cancel. And exactly the same as before. Why is there a pole when z1, z2? When y, z1, z2 goes to 0, it's just exactly the same things, because we're taking the intersection point of 1 and 2, and we're moving to lie on the line at infinity. Okay? I is going from 1 to 3. I is going from 1 to 3. The z's are 3-dimensional vectors. Okay? This is it's a P2, so the z's are all 3-dimensional vectors. Okay, these things are super simple. Okay, almost all these things are super duper simple, but that's the point of these couple of classes. You should do these super simple things, and then after a while, we're going to be flying back and forth between the space and the dual space and this and back and forth and intersecting things. We're just going to do that all day long, right? So you should you should play with these very, very, very simple things, and also the problem set that I keep promising, but which has not appeared, will have a lot of questions like this on it when I manage to come up with a good enough set. I promise to give it to you on Tuesday. All right. So let's actually keep going with this picture a little bit. Remember, in projective space, we have this duality, where we can interchange points with lines and lines with points. Okay, so it's very useful in any picture you have to look at what the dual picture looks like. Okay, and it's just reinterpretation, but we're going to see that that it's going to be very useful for us. So let's take this picture. Y is at infinity. By the way, I've drawn this picture in a particular way, where the line at infinity does not cross the triangle. What would it look like if the line at infinity did cross the triangle? If you tried to draw a picture of the line at infinity crossing the triangle, what kind of triangle would it look like? Okay, it would look like some funny triangle that goes out from a vertex here, boom, and comes back, goes around infinity and comes back. Okay, so it wouldn't be a triangle that fits in your picture. It goes to infinity. It intersects infinity, right? So it's manifest that in all the pictures of areas that we're talking about that are reasonable, the y is outside the triangle. Right? In particular, it's at infinity. So, and for example, it tells us in particular that y, z1, z2, and so on are positive numbers when we draw the picture like this. Then I think of it, if I think of it as a function, I can move y around. It has a pole. You can even go to the other side of the pole. It can be negative. Okay, but where we have the geometric interpretation of it directly as area, we have to have that all these y's are positive. All right. Now what I want to do is draw the dual of this picture. So what is the dual of this picture? Okay. In the dual of this picture, everything that's a line is a point, and everything that's a point is a line. So z1 is a point. Here's a point z1. z2 is a point, and z3 is a point. So I have a new triangle in the dual. Now, y is also a point, right? Where do you think y is in this picture? It's inside the triangle. Okay? And why is that? Well, exactly this. We have to have that y, z1, z2 is positive. That means that y is on this side of the line 1, 2. It's on this side of the line 2, 3. And it's on that side of the line 3, 1. Okay, so the line outside the triangle means the plane at infinity outside the triangle means the point inside the dual triangle. In this case, the triangle is a triangle, its dual is a triangle. In more complicated spaces, the duals don't even have to have the same shapes as each other. Anyway, we'll get to that later. Okay. All right, excellent. So that's it. We have a formula for an area, or we have a formula for an area over volume, and we can also think of it dually as some formula that if you give me a point inside a triangle assigns a function to it, and you can think of that function as the area of the dual of the triangle. Yes? No? Well, sorry. If you fix what it is here, then of course I know what it is there. Okay? Sorry? Well, it does matter because, so let me just say, what I'm doing on this side is on this side, I'm telling you this function has an interpretation that you're familiar with. Okay? It's interpreted as the area of the triangle where you think of y as the plane at infinity. Okay? And so if you do that, the concrete way you would do it is you say you would do an SL3 rotation to put y equals 1, 0, 0, and then it's literally the area of the thing that's left, the familiar area of the thing which is left. All right? Now, here I'm saying something a little different. I'm saying that in this dual space, I have a point y. And given this data of the z's, that gives me this triangle, and some point in this space, I'm associating a function to it. Right? Now, what is the interpretation of this function? At the moment, the only interpretation is it's a function that's the volume of the dual. Okay? Later, I'm going to give you a direct interpretation directly in this space. Right? For now, I just want you to get used to drawing the pictures, what the pictures look like in the space and in the dual space. Okay? Right. If you like, exactly. That's right. You choose a line here, there's a point. You choose another line that doesn't intersect the triangle, you get another point. Right? As you move this line around so that it gets dangerous and it touches somewhere, then that means here it's doing the same thing, right? Okay? All right. Okay, so now that we have a notion of area, let's just play in 2 dimensions a little bit. And let's look at slightly more interesting areas. So let's look at quadrilateral. Every time I try to draw lines that aren't parallel, they're parallel. OK, so here's I just suck. All right, these are pretty parallel. All right, so let's say I have a quadrilateral where again I'm giving you the edges for now Z1, Z2, Z3, Z4. Okay? And now I want to know, so again, the Z's are the edges here. I have my line Y at infinity. Okay? And I want to know what is the area of this quadrilateral. Now, how would you do it? You could just do it as the sum of the areas of triangles, right? Actually, we'll do it both ways, but I'll do it in a slightly different way to begin with. I'll look at it as the area of this triangle minus the area of that one. Okay? Beautiful triangle. That's awesome. Oh, that suck. Slightly better. All right. So the area of 1, 2, 3, 4 is equal to, well, it's this big triangle, which, now, what are the sides of that big triangle? Are Z1, Z2, and Z3. So let me write that as the area of 1, 2, 3. And then I have to subtract this one. Now, what is this one? This is 1, 1, 4, 2, right? No, sorry. I want to do this one. So I did 1, 2, 3 minus 1, 4, 3. Okay? Now, something important we should have commented over here is that this is a signed area or signed volume. So it also comes with an orientation. Okay, so if I interchange any 2 of the z's, we pick up a minus sign. Okay? So that's why I'm giving you I'm orienting all my triangles clockwise like this. So 1, 2, 3 minus 1, 4, 3. Yes. The z's are these edges. Okay? And now what I've done is draw a bigger triangle. So what's special about this triangulation is I'm not introducing any new edges. I'm introducing a new point, but I'm not introducing any new edges, right? So the big triangle has edges Z1, Z2, Z3. The small triangle has edges Z1, Z4, Z3. Is that OK with everyone? All right, so it's 1, 2, 3 minus 1, 4, 3, which is also, by antisymmetry, the area of 1, 2, 3 plus the area of 1, 3, 4. OK, now, so just because we're practicing, let's see what does this triangulation, funny triangulation, look like from the perspective of the dual. What's going on in the dual picture? Now I have a quadrilateral whose vertices are Z1, Z2, Z3, and Z4. Okay? Y is inside somewhere. I don't care where. But now what are these things? This is that triangulation of the quadrilateral itself. See, this triangle, Z1, Z2, Z3, corresponds to the triangle in this picture whose vertices are 1, 2, and 3. And the other one is 1, 3, and 4 is the other one. And now you see in this picture the orientations automatically work. I didn't have to flip any signs. So already there's a cool, very simple general fact. If you give me a triangulation of a polygon, more generally polytopes, but we'll talk about them later. Just here they're just very familiar polygons. You give me a triangulation of a polygon. It also gives me a triangulation of the dual polygon. But here we have this external triangulation where we have new vertices, no new edges. And here it's the other way around, right? Here we have an internal triangulation where we have no new vertices but new edges. Okay? And I'll leave it as an exercise for you to do it the other way around. Okay? So of course you can triangulate the other way around and get similar expressions. You'll do that on the famous problem set. Okay. So yeah. Yes. So I'm drawing this particular convex quadrilateral. Okay. So and we're not talking about some funny shapes. We can talk about funny shapes later. I'm just literally drawing the shape you see. We'll come in a moment to what shape means more generally. Okay. But here, just for this lecture, it's just familiar things, right? Just things that look like convex, polygon, simple quadrilaterals like that. Okay. Yes. 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 Here, y is outside. Let's see. Yeah, no. So that, yeah. So if we look at, well, first, yeah, I think, yeah, yeah. So let me. Then you don't have your complaint, okay? And we'll come we'll come to the question about exactly what this means a little bit later, okay? So yeah, but yeah. So indeed, if I put it here, it corresponds to y being in one of the triangles and not the other, and I could yeah. That's exactly why I was trying not to draw y in this picture. I didn't want to talk about that right now. I promise we'll talk about it. We'll talk about it later. Okay. So okay. So what I now want to do is look at the. What I want to do is look at the formula. Okay. So what is a of 1, 2, 3, 4? Well, the first term is 1, 2, 3 squared over y12, y23, y31. And the next term is 1, 3, 4 squared over y13, y34, y41. Okay? And we see the we see the kind of basic thing that we've talked about a lot. Each term has a spurious pole, right? The poles we should have are when yi plus 1 goes to 0, but each term has a spurious one. Where y13 goes to 0. Right, and that's obvious because we've introduced, in either picture, we've introduced this artificial point here, which is the intersection of 1 and 3, or this artificial line, which is the line 1, 3. and something blows up when we have y13 goes to 0. That's a spurious pole that cancels in the sum, right? I mean, clearly, this is just our way of doing the triangulation. We could have triangulated it another way with 2, 4, and then we'd have had a different expression, right? So we could also say that A 1, 2, 3, 4 is also equal to the other triangulation, right? 1, 2, 4 plus 2, 3, 4, for example. Okay. All right. Sorry. Yeah. No. Z1 and Z3 are not parallel. Z1 and Z3 are only parallel if the lines meet at a point at infinity. Okay, and so when y13 is 0, what's happening is that the triangle is becoming big. Two of the sides become parallel. That's why you get a divergence in the area. Okay, so on the one hand, we have this expression like 1, 2, 3 plus 1, 3, 4, but there's nothing special about 1. There's also an expression 2, 3, 4 plus 2, 4, 1, for example. Okay, so we have two different expressions, but this one has a spurious pole term by term. That's when y13 goes to 0. This one has a spurious pole when y24 goes to 0. Of course, they cancel in the sum. So there's this interesting 4-term identity that these areas satisfy, which is that this plus this equals that plus that. And we can use that identity, well, trivially to see. In this case, it says that every way of writing the answer is the same, and the spurious poles have to cancel. But let's see explicitly how this happens in this case, and let's make some more comments about this object. So I want to put everything under a common denominator. Let me call it y13. OK, so what do we have upstairs? From the first term, we have 1, 2, 3 squared, and then y34, y41. And then I'm going to have 1, 3, 4 squared, y12, y23. All right. So we're going to stare at this guy for a little while. So let me call this numerator n. Now, before we do anything else, let's just think for a second about what the structure of the final answer should be. Because that's already a little instructive, right? So what should the final answer look like? A of 1, 2, 3, 4. Well, we know it certainly will have poles when y12, 2, 3, 3, 4, or 4, 1 go to 0. But what's wrong with this formula? Like, why can't they just write this down? Apart from it has some funny weights in 1, 2, 3, 4. Okay, so it has that problem. But what other problem it has? It has the wrong weight in y. Right, remember, areas here have weight -3 in y. I'm summing things with weight -3 in y. This thing has the wrong weight in y. Okay, there's weight -4 in y. So whatever the heck the final answer is, it has to look like y, which has a downstairs index, times something. I don't know what I should call it. Some p, which is a point, with an upstairs index. All right? So just keep that in mind, right? So somehow, out of this problem, we have to find a point. Okay? So somehow we've got to get a point, and that point has got to go in the numerator. Now, just relax for a second before deriving anything. I have this quadrilateral. Let me just draw it back in the original space, right? So here I have Z1, Z2, Z3, Z4. My goal in life is to make a point out of this data. How would you make a point? Yup. That's the answer. Okay. You intersect those two diagonals. It gives me this point P. So who is that point? This point P is 1, 2 intersect 3, 4. Right? This is the point 1, 2. Right? This is the point 3, 4. So I have to first make that line, which is 1, 2 intersect, which is 1, 2, 3, 4. This line. And then I have to intersect that with, so let me write it like this. It's 1, 2. And then I have to intersect that with 2, 3, and 4, 1. Okay, so this is the point that I'm trying to get. Let me write it again. So this is 1, 2, 3, 4, intersect 2, 3, 4, 1. Is that clear? So this is what the answer is going to end up being. But let's now forget about it and come back and see how we can get it. All right, now when you're playing with expressions like this, there's sort of lots of different strategies. The basic problem that we've seen over and over again is that these brackets satisfy quadratic identities. These brackets satisfy those Plücker relations. Right? And so you can have an expression, but a given expression can be expressed in many different ways. We saw that when we talked about intersections of points and planes and so on, that we could write those formulas in a number of different ways, and they're all the same on the support of these identities. So one thing you can do is to just keep those identities in mind and use them all the time. Another thing you can do is to choose some specific set of variables or coordinates, and then do your manipulations at that level, and then at the end write everything back in a coordinate independent way. So these are all just strategies. So what I like to do when I encounter situations like this is to just take whatever is to use coordinates tailored to the problem, obviously. So in this case, we're interested in seeing why it is that this numerator vanishes when y13 goes to 0. Okay? So let me, to do that, y is just some y is a line, 3 and 4 are lines. Dually, they're all points. Okay, so I can certainly expand y, I, as I'll call it alpha 1 z1 I plus alpha 2 z2, z3 I plus, and let me call, now this is kind of canonical because I'm interested in what happens when y goes on the line 1, 3. Right? So I care about 1, 3, so I'm doing the expansion like this. This thing is not canonical. I mean, I have to have some third point, some third z to put there. I could, for example, just put some z star, just a random z, and then the star should cancel out from the calculation. But I can also make my life easier and choose it to be one of the z's. So the only other ones I can do, 2 or 4, let me choose 4. Okay, and that'll just it'll make things, some of the terms will cancel to begin with. Now, normally when we do this, of course, the y's are defined up to rescaling. So the alphas overall also define up to rescaling. So I'm always free, for example, to use that freedom to set alpha 1 to 1, let's say, or z4 to 1. I can in principle scale any of these things to 1 in some chart. Here I'm not going to do that. So it doesn't matter that much. I'm not going to do that because keeping them around helps me remember what weights things have in y. Okay, so all of these, for example, alpha 1 is something that has weight 1 in y and minus 1 in z1, right? Because the whole thing has to have the same weight as y. Right? Anyway, we can, of course, trivially write down a formula for alpha 1, alpha 2, and beta, right? So I can just solve. This is a vector written as a linear combination of 3 vectors. So for example, alpha 1 is equal to y z3 z4 divided by z1 z3 z4. If I just contract both sides of this equation with 3 and 4, then I get this. Alpha 2 is equal to y z1 z4, the minus sign, over z1 z3 z4. And beta is y z1 z2 over z1 z3 z4. So I'm going to play with I'm going to shove this parameterization into the numerator, and at the very end we will we'll get some expressions with the alphas and betas, and we'll just put them back in that form. All right, so let's look at the enumerator now. So the enumerator is the first term is 1, 2, 3 squared. What is y34? So y34, I'm contracting this with 3 and 4. And so that's very nice because these terms drop out. So I'm just going to get that term. So y34 is alpha 1, 1, 3, 4. Now, the next term is y41. Y41 is also simple, right? Because now 1 and 4 drop out. So I'm just going to get alpha 2 341. So let me put a minus sign in front of the whole thing. 1, 3, 4. Oh, sorry, I should have called this alpha 3. That was dumb notation. All right. What about the second term? We have 1, 3, 4 squared. Okay, so now this one's going to be slightly more painful. The first term, y12, only the 1 drops out. But we're going to get alpha 3, 1, 2, 3, plus beta 1, 2, 4. And then from the second term, y23, we're going to get, again, alpha 1, 1, 2, 3. The 3 piece goes away, and then we're going to have plus beta 2, 3, 4. OK, so yes?
Can you help me understand why there's a 1, 2 in your beta and not a 1, 3?
Oh, that, because I wrote it wrong. OK. All right. OK, so now, the whole point is that the alpha 1, alpha 3 term cancels. Right, there's an alpha 1, alpha 3, 1, 2, 3 squared, 1, 3, 4 squared, also upstairs. So that term cancels, and what am I left with? I'm left with things that just have a beta in front of them. Right? That's good, because beta is exactly y13. So that's good. We have to have a 0 upstairs to get rid of that spurious pole. But let's just see what the whole thing looks like now. So this first term takes care of that one, and we're just left with everything else. So this has an overall beta, a 1, 3, 4 squared. OK, and now I have 3 terms, right? One term is one term is alpha 3, 1, 2, 3, 2, 3, 4. Then I have plus alpha 1, 1, 2, 4, 1, 2, 3. And finally have plus beta 1, 2, 4, 2, 3, 4. OK? All right, very good. So we can now plug everything back in. We can now plug back in the expressions for alpha and beta. And what do we get? So we get, so numerator is equal to just y31 sorry, y13. So that eats up one of the 1, 3, 4s. But then all of these alphas have a 1, 3, 4 in their denominator as well from those formulas. So all the 1, 3, 4s are gone. Okay? So there's no 1, 3, 4, and the rest I just read off. Okay? So I have the term alpha 3, 1, 2, 3, 2, 3, 4. Alpha 3 is y34. So I have y34, 1, 2, 3, 2, 3, 4. Then I have alpha, sorry, that was with a minus sign. Alpha 3 had a minus sign. Then I have plus alpha 1, which is y34, 1, 2, 4, 1, 2, 3. And then I have plus y13, what was that? 1, 2, 4, 2, 3, 4. OK, beautiful. So the y13 cancels? Yes. Yes, I'm sorry. OK. All right, and so the final answer is just as promised, is y12, y23, up to y41, multiplied just by this guy, right? Because y13 cancels. All right, so that's some interesting expression, right? It's linear in y, had to be linear in y, so this is producing a point for us. And that point is exactly 1, 2, 3, 4 intersect 2, 3, 4, 1. Right? So let's see how we'd go about computing that point using okay, so if I look at 1, 2, 3, 4, well, 2, 3, 4, 1, and y with this bracket, then there's various ways of I can think of this guy as first as 1, 2, 3, 4 minus 2. Actually, the whole point is that there's various ways of doing it. So first let's look at 1, 2. Let's first look at this 1, 2, 3, 4. So what is this guy? This guy is Z1, 2, 3, 4, minus Z2, 1, 3, 4. Of course, I can also write it the other way, right? I can also write it as negative Z3, 1, 2, 4, plus Z4, 1, 2, 3. So this was the most basic thing we saw last time. You can have an invariant object, the intersection of two lines, and yet any explicit representation of it always gives it to you as either some linear combination of points on one line or the other line. Right? So we have to get used to this all over the place in this business, that they're invariant objects, but every reasonable representation of them often doesn't make their invariance manifest. Okay, so this is already the most primitive example. Okay, so I'm going to use this representation for 1, 2, 3, 4, and I'm going to use this representation 2, 3, 4, 1 is equal to Z4, 1, 2, 3 minus Z1, 1, 2, 4. Okay? And so what is y 1, 2, 3, 4, 2, 3, 4, 1 is y. The first one is 2, 3, 4, 1 minus 1, 3, 4, 2. The next one is 1, 2, 3, 4 minus 1, 2, 4, 1. Sorry, I screwed something up here. Sorry, this is 2, 3, 4. Let me make sure I did this one right. Yes, this is right. Minus 2, 3, 4, 1. And so you see I get 3 terms. I get y 2, 3, 4, 1, 2, 3. I get 2, 3, 4, 1, 2, 3, y 1, 4. 2, 3, 4, 1, 2, 3, y 1, 4. I get 2, 3, 4. This one cancels because that's 1 and 1. I get 1, 3, 4, 1, 2, 3, y 2, 4. I don't have, oh, because I did the wrong one. I was supposed to do, I apologize. I meant to do the other one for the top one. 1, 2, 4, Z3 minus 1, 2, 3, Z4. Sorry about that. Okay, so let's take that check mark off. All right, so let's do it again. So, so we get 1, 2, 4, 1, 2, 3, y3, 4. That's good. We get 1, 2, 4, 2, 3, 4, y3, 1. That's good. And we get 1, 2, 3, 2, 3, 4, y4, 1, which is, sorry, we get the, sorry, this one, which is that one. Oh, sorry, we did that one, which is that one, the y1, 4. And the fourth term is 0 because I'm contracting 4 with itself. Okay? And all the signs work out. So I did this exercise once in gory detail so that you see how these things work. The terms can be put together. The spurious poles cancel. Any representation will look a little asymmetrical, could look a little asymmetrical, but has a completely invariant interpretation, right? The numerator is y dot this special point where the is y dot this special point where given by the intersection of the diagonal lines. Now, this is interesting. The area has a pole in an obvious place when the sides become parallel and the thing becomes infinitely big. But it also has some interesting zeros, right? So why don't we think about those zeros normally? Well, the zeros are a little bit funny, right? In order to access that zero, that point is inside the polygon, right? The point is inside the polygon. The whole point was infinity is outside the polygon. So in order to see the 0, we have to continue past the point where we have our obvious standard geometric intuition for what it looks like. Okay? Nonetheless, the 0 is very interesting. And we're going to interpret it again in a different way in just a second. But just taking stock, what have we seen up to this point? We've seen that, that we have these projective areas. Really just ordinary areas, but we're thinking about them projectively. We can form more interesting regions. For polygons, for example, we can triangulate. They have term-by-term spurious poles. That cancel in the sum. The building blocks are these 1, 2, 3s, which satisfy a 4-term identity. Which was this 1, 2, 3 minus 1, 2, 4 plus 1, 3, 4 minus 2, 3, 4 equals 0, which was simply the fact that we can cut up the square in 2 different ways. And if we were just to talk about the poles are obvious. The zeros are interesting. and we'll come back and talk about them. But let's proceed. What can we say for the general? What can we say for a general n-gon? Well, the area of a general n-gon of sort of 1, 2, 3 up to n. So let's say I drew a pentagon. Now, of course, I can triangulate this in a million ways, but so I want to have the analog of this formula, 1, 2, 3 plus 1, 3, 4. Now, remember, 1, 2, 3 plus 1, 3, 4 was this interesting external triangulation, but we could think of it dually as an internal triangulation of the dual. The dual of a polygon is still a polygon, right? So in this picture, if I'm drawing the dual just to represent what the triangulation is, so Z1, Z2, and so on, Zn, then the kind of simplest thing you would do is to just send out all the rays from 1, right? Just send all the rays from 1. That'll triangulate the space. And so we would get one formula. There are many, but there are one formula that would look like a sum over I of this basic area 1 I plus 1. Right? And if you recall, our basic our basic 1, 2, 3 is 1, 2, 3 squared over y1, 2, y2, 3, y3, 1. Now, right here, let's go back to our toy amplitude that we talked about and remark again the remark I made at the end of last lecture, how similar this looks to the formula for the amplitude. They're still not quite identical, but they're damn similar now. The bracket that we wrote for our toy amplitude, so this is now our toy bracket, just so I just write 3 things rather than 5, was also the square of something, but upstairs it had this structure, 1, 2, eta 3, plus 2, 3, eta 1, plus 3, 1, eta 2, squared. And downstairs it just had 1, 2, 2, 3, 3, 1. So they look rather similar. There are some seemingly big differences. Here, there's a y, right? And also here, the z's are 3 vectors. Yeah. Here. No, this is just the definition of the object we're talking about, right? So the area does depend on y. So there's some, we're talking about an area or a volume, and the notion of volume depends on this choice of a plane at infinity. So this thing does depend on y. Back in our world of amplitudes, there's a clear similarity between these two things, but there seem to be 2 differences. One of them is that here the z's are 3 vectors. The other one is that there are some etas here. There's etas here, there's no etas there. There's a y here, there's no y's there. And there, in fact, that's exactly the clue for how they're related to each other. Okay, so roughly speaking, and we'll see it more precisely in the next lecture, the z's that are, so y defines a special direction. So once you tell me what y is, I can always rotate to make it look like 1, 0, 0. So y defines a special direction. And so in the 3-dimensional z's, there's that part that's in the direction of y and the part that's not. The part that's not are 2-dimensional z's. Those are going to map to our 2-dimensional z's in this problem. But then there's this extra component in the z, the one that's in the direction of y. And that extra component is going to be where all the Grassmann-Suzy stuff lives. Okay? Except it's dealt with in a completely bosonic way. So this is, amongst other things, a totally bosonic way of doing supersymmetry, where you can defer until the very, 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 very end, getting Grassmann stuff out of totally bosonic objects. And in fact, when we interpret it even better, and we'll do all of these things next time, when we interpret it better, we'll actually interpret them, these amplitudes, even this formula is going to be upgraded and slightly reinterpreted as a differential form instead of a superfunction. And when we think about it as a differential form, everything will just be classical geometry. There's not going to be any super stuff anywhere. Okay? So we're going to bosonize the supersymmetry entirely. Okay, but let me just do, yeah.
When I go back home, I'm going to try to do these calculations tomorrow. And
forget about y. So that's it. Forget about drawing anything with the y. Just treat the triangles. But now what you're going to do when you get the internal triangulation is you have to use a formula for the area of the triangle where you know the vertices rather than when you know the edges, right? I gave you both formulas, right? We gave a formula with vertices and with edges, and so that's the difference. You'll get a very different looking formula. It's actually interesting. In this formula, you're not going to have any spurious poles, right? By construction, you're not adding any new because you're not adding any new vertices. The only way in the internal triangulation, the only way you get a divergence is when one of the vertices goes to infinity. I'm not adding any new vertices, so I'm not getting any new poles. So this is a totally different kind of triangulation where you don't have spurious poles, but you have other problems. Okay, so that'll be explored on the problem set. I'm not doing the second kind of triangulation. It's very important. We might say something about it later in the course, but just so you know where this is going, it's going to turn out that all the terms that we see at tree level in BCFW are like this kind of triangulation that we talked about. They're a triangulation that sort of naturally lives in the space where the z's are not lines but are points in the dual. Okay, and so that's why I'm focusing on this kind of triangulation. The other one's also interesting. Let me just do two other things quickly here. So these were so this is the formula. All the spurious poles cancel, et cetera, et cetera. Can we guess? Is there a simple picture for what the analog of this numerator is in general, right? So now, in order to do that, let me actually go back and reinterpret that numerator. So remember, we started off with this kind of picture, and we said that the numerator is associated. The numerator is associated with this point, right? So what does that look like in the dual? So now in the dual, I have Z1, Z2, Z3, Z4. Okay, so here, P is a line. Okay. So what's the line? Well, what's the line that I can make out of this problem? These two edges, which don't actually meet in the quadrilateral that I'm interested in, do meet at this point up here. So there is one point, which is the intersection of 1, 2, and 3, 4. And these guys meet at another point, 2, 3, intersect 4, 1. Okay, so this line in the problem maps to one of those points, and this line maps to another point. And so this point is nothing other than this line. Okay? So again, somehow in this picture, as we said, y is inside. So if y stays inside, everything is fine. But if we continue the function, it actually has a 0 on this interesting line, right? And what's cool about that line is that if I only told you that if I didn't tell you anything about what the if I didn't tell you anything about the actual shape of the quadrilateral, but I just told you I have a bunch of lines 1, 2, 2, 3, 3, 4, and 1, 4, then there's many regions that you could draw, right? And there are lots of and so there are many interesting places where those lines of the form I plus 1 intersect. In this problem, there are 6 of them. These 4 are good ones that we like. They are corners of our quadrilateral. And there are 2 that are bad. And the numerator is exactly a function that's 0 on all those bad ones. That's what we found, right? Now, at the moment, we don't have a sort of particularly good understanding for why this is true. Next lecture, when we talk about canonical forms, we'll understand why this has to be true. fact, so we'll have even a direct way of writing down the answer. At the moment, it's just an amusing observation that we've seen that the 0 of the area is associated with a function that in the numerator that has a 0 in all of the intersections of the lines that are actually not in the geometry that we like. Okay, so just using that, let's see if we can make a guess for what the area of a pentagon should be. So let's say you have a pentagon now. And now, again, I'm drawing the dual of the pentagon. So I'm going to have some Z1, Z2. Because I'm so bad at this, let me cheat a little bit. When you work in this stuff all day long, people in airplanes think that you worship Satan. And hexagons don't help that much either. But anyway, this is definitely not a good start. So here's my pentagon. Here's the pentagon that I care about. This is, again, the dual pentagon. So the vertices are Z1, Z2, Z3, Z4, and Z5. All right. I've drawn a bunch of all the other interesting points of intersections of the side lengths of this pentagon, which are now 5 of them. This guy, this guy, this guy, this guy, and that guy. OK? Now, let's think again what the formula should look like for the area. Now it should have 5 poles. So the area should look like y12, y51. Again, I want to stress how unusual it is that we're thinking about the poles of the area, of the function of the area, because tacitly in our minds, we're now thinking of this as a function of this line at infinity, y. Right? So thought of as in terms of why we care about the poles and zeros of this guy. All right? All right. But following at least the analogy from this case, and what do we need upstairs just by weights? We need 2 y's upstairs, right? So whatever the heck it is something that looks like Cij, Yi, Yj. So remember, in this dual picture, the y's are points. So the Cij, what is a Cij? It's a symmetric tensor. What is a symmetric tensor in the projective space? It's a conic, right? So Cij fixes some conic. What is the job of this conic? This conic needs to have a 0 on these 5 points. Well, fortunately, there's a unique conic that passes through 5 points, and we're done. That's the numerator. Okay. So that's a remarkable formula, right? That if you want the area of a pentagon, you draw the dual of the pentagon, you write all the poles downstairs, then you find the conic that passes through these 5 points. That's it, right? Once again, as in our and for any polygon, this is true. There's a unique curve of the appropriate degree that goes through all of the bad intersections. Okay, and that completely determines what the area of a polygon is. With no triangulation, no reference to any way of cutting it up. So this is a sort of completely invariant way of determining what the answer is. I haven't justified for you why it has these zeros. When we reinterpret the volumes as related to canonical forms, we'll understand why it has to be the case, right? But so already you are seeing some of the features that we're going to be, in these very simple examples, that we're going to be seeing more and more, that there are natural geometric questions. These questions have, there are some rather beefy answer to this question. So even something as dumb seeming as the area of a polygon, right, as an expression as a function of all the variables, some kind of juicy expression, right? We can break it up into simple pieces. If we do that, we can do it in zillions of different ways. There's no canonical way of doing it. They're all equal to each other. There is some invariant, though, right? The invariant is the boundary of the polygon. If I triangulate, I have to make sure all the internal boundaries cancel. So there is something that there is an invariant definition of what the object is. Even independent of triangulation, even if you get the answer somehow, as we've seen here, in order to recognize it, if someone just hands you the final answer, in order to, it may not be easy to explicitly recognize it as the answer to an invariant question, simply because any representation of these interesting points and conics and so on often involves making making choices. Okay? But it doesn't change the invariant fact that the answer is totally symmetrical. It has all the symmetries, the cyclic symmetries in this case, and so on. Yes?
Could there be some kind of assignment there? So it looks like magic, right? So could there be some way, or did I miss something? Could there be some way at the start in the theory in which it's obvious that the answer is polygons, like
it depends the level of ambition that you want the answer to that question, but that's essentially exactly what we're going to be doing for the next month. Okay? Is building up to an obvious question. Well, we're gonna build obvious objects and ask obvious questions of them. Here it's a little too simple. Here all we see is that if we ask this question of the area of the polygon, we get an answer that has poles that look like I plus 1. All right, so that maybe doesn't seem so super impressive. It might even seem that we almost put that in by just asking that I'm talking about a polygon to begin with, right? But well, yeah, then as we go to already as we stick in this kind of world, just the generalization of polygons into higher dimensional shapes, into polytopes is already more interesting. And actually, there's something we slid into it so quickly here that we had an ordering on the z's that we liked, and we just drew the polygon with the vertices in that same ordering. Okay, so nothing told us to do that, other than the fact that there are two orderings, and so we didn't see any reason to make a different choice. So we actually have to go back and think what ordering means and how ordering is related in this picture to some notion of convexity and ultimately to a notion of positivity. Once we have that, so we have ordering on the external z's, and once we have ordering on the external z's, there's a natural notion of positivity associated with it that in this very simple case tells us to draw a polygon. If we now ask for higher dimensional vectors, it tells us to draw much more interesting shapes that are not so super familiar to us as a physicist. They're ancient objects that have been studied for over 50, 60, 70 years by mathematicians, just in this case where we're generalizing polygons to more general polytopes. These objects that are polytopes where the vertices have a natural cyclic structure on them are known as cyclic polytopes. And if you now just ask, nowhere did you say anything about I plus 1, jj plus 1, any of these properties, the poles that it should have in order to look like space-time amplitudes. You just have your data is n ordered n vectors, n four-dimensional vectors with an ordering, and you have a certain positivity requirement on them. Go. Okay, just go and see what is the volume of this polytope or the dual of this polytope look like, and you'll get exactly the answer that we interpret as the NMHV scattering amplitude, including the fact that the only poles are I plus 1, jj plus 1, which is space-time locality. Nowhere do you put that in by hand. That's a consequence of this, essentially the only question you can ask on this space. Okay? So the not in any there's many kinds of positivity here. There's the positivities that there's the usual positivities that we know and love that have to do with positive norms, right? And that's I think something in general, most positivities we know of in physics have two sources. Energies are positive or probabilities are positive, and they have various consequences. This is, on the face of it, something totally different, right? This is well, those things turn out to be special cases of it, exactly. But they turn out, I mean, much more special. I mean, the entire amplitude is essentially fixed by this requirement of positivity when appropriately interpreted. You go to some space with some positive structure on it. You ask a natural question on that space, and that question has all the properties as a function of these z's that we would normally ascribe to local unitary evolution. So it has poles in the right places. It factorizes in the correct way. All of those things are actually just a property of the geometry. Okay? So we did not know it had to happen. We did not know that it had to happen ahead of time. We asked this question in this space with where the only structure we have is n four-dimensional vectors with an ordering. Okay? We ask a natural question in that space, and we discover the answer to that question has all the properties that we normally associate with local unitary evolution in space-time. That's the entire philosophy of this of what we're talking about in the course. Is Yeah, but we don't a priori know where it comes from. Yeah. Sorry? Right, right. Exactly. That's right. No, we don't know. No, we don't. But what we're going to see here is that, and all the examples we're going to see, that there's a couple of ideas involved, but positivity is certainly a very, very important one. So there's some notion of positivity, so that notion of positivity is first associated with something almost purely combinatorial, then something geometric, then something analytic, which is what we attach, what we interpret as the amplitudes. In this case, if I had to say those words, the combinatorial part is a little too trivial to even say. But although it's important that it follows, it's that there was an ordering on the z's, and the space that I'm talking about has the vertices ordering the same way that I had the z's ordered. So that's the first part. Then there's a geometric shape, which is the polygon. Polygon is a polygon is a polygon. Then there's a function associated with it. The function associated with it, which in this case is the area or the area of the dual. Okay, so those are the sort of three things associated with the space of two-dimensional z's. Or if I give you the space of three-dimensional z's with a y, or I can interpret it as a space of two-dimensional z's plus supersymmetry. Okay, so those things will be closely related. But that's my toy kinematical space in this model. The toy amplitude looks like some weird function, but I then interpret as the area of this polygon. And why I drew the polygon is dictated by positivity conditions that I've not yet talked about explicitly. Okay? So that's what we'll be starting with next time. So here I started just by reminding you of your sort of high school formula for the area of a triangle, and off we went from there, and we discovered that these areas had areas and volumes had interesting properties. Next time, we'll begin by actually justifying that it's an area, by showing that it's the integral of something. So, and to do that, we'll have to talk about differential forms on projective space. So the first thing we'll do is just talk about how you write differential forms in a projective space. We'll write these volume integrals down. That part will be trivial. But then there's going to be a second kind of interesting object to talk about, which is when you take one of these pictures, like this one, now literally in the space where the z's are vertices and not lines, in this space, in the two-dimensional space where the y's are a point now, I'm going to look for a certain differential form. So you give me this polygonal shape. I'm going to look for a differential form that has the property that has singularities on the boundaries of this shape. Now, what that means most loosely is that it has poles when you hit the sides. But we want to know more. We want to know that that's something that's really tailored to this particular shape. And so we have to talk about the notion of a residue. So we have a pole, but if we take a residue on the pole, instead of having a two form that's defined everywhere, we'll have a one form. For example, if I take a residue on the pole where y goes on this line, we'll end up with a one form, and that one form in turn should only have singularities at the endpoints. So this is a stronger requirement on the form. You give me a shape, and then tailored to the shape is a unique canonical form that has the property that it has logarithmic singularities that allow you to take residues all the way down to all the points. Okay? So we'll review that idea. I'll show you how it works in the simplest cases of intervals and triangles and so on. And then we'll move up to these examples. So this is a second way of associating now not a function but a differential form with some geometric shape. And I'll tell you what the connection is between the second way and this more familiar notion of area. They're dual to each other in an interesting way. So once we get all of that under our belt, we're sort of done with our zeroth order pass through the projective geometry, and then we'll go back to thinking more from closer to first principles about scattering amplitudes, lambdas and lambda tildes, momentum conservation, and start talking about the Grassmannian. All right, thank you.